Hello and welcome back to Calculus 2. I was about to say 3 for some reason. Because section 8.3, infinite series. That's why. So we are going to take the lists from last class, ordered list of numbers, and we're going to add those numbers. Now, the intuition might say, if you add infinitely many numbers, they should add to infinity every time. But they don't. In some cases, infinitely many numbers add to a half, add to pi over 2, add to 10. And sometimes they add to infinity. So we studied the concept, that kind of concept, as infinite series, where we take the sequence and we add all of the terms, and then we study the properties of that sum. So we start with the definition. Series is a sum of a sequence. Sum. So the notation for it is summation an, where n can start, let's say, at 0 and go to infinity. That's a notation. And what it means is a0 plus a1 plus a2 plus a3 plus a4 plus ... going on forever. Now, we do have finite series. If you write summation of, let's say, n goes from 0 to 3 of n squared minus 1, well, that is going to be -1 plus, for 1 we have 0, plus for 2 we have 7, and for 3 we have 26, right? So this is called finite series, and because it has finite number of terms, they always converge, because if you have 4 terms or 10,000 terms or 100 million terms, it doesn't matter how many you have, it's a finite amount of them, and then you either use, you go add them by hand, or you add them using calculator, computer. So this is 32. So finite series, they always converge. And because they always converge, we don't study them. There's nothing to study there. It's just a bunch of numbers that are added, and depending on how many you have, you add them by hand or you add them with the add of technology. Done deal. The infinite ones are the ones that are interesting, because you can't be sitting there for eternity, we're not elves, adding all of these. We have to add using clever methods. So what we have are 10 different tests that we study in this class. There's more, obviously. We study 10 basic tests to test for convergence or divergence of series, which means what's going to happen to the entire series as you add infinitely many terms. So in some cases, we will be able to compute the number they converge to, and in some cases, we will only know if they converge or diverge, and that's it. We don't know what they converge to. Now, for most part, we can approximate using technology, adding a lot of terms, but you will never have exact number until you actually add all of them. So if there is no clever mathematical way to determine what they converge to, you will either have to be satisfied just with the knowledge that they converge, or with the approximation of stuff that you get. So let's see. what does it mean for series to converge? Again, this is not honors section of calculus class, but you know, I'll show what it means for series to converge, and then from that point on we will be looking for convergence or divergence. So here it is, what it means to converge. Say you have infinite series an and you are asking if this is convergent or divergent. So what you could do is find a sequence of partial sums. Find the sequence of partial sums, and then if that sequence converges, the series will converge. If that sequence diverges, the series will diverge. It is very dangerous in this class in this chapter to draw conclusions between the two worlds of sequences and series, but sometimes we have to do it. So first partial sum, S0 is just a first term A0. S1 is A0 plus A1. S2 is A0 plus A1 plus A2. S3 is A0 plus A1 plus A2 plus A3. And now I got bored. Which creates the sequence of S0, S1, S2, S3, S4, going on forever. So now that you have this sequence we know how to deal with this, right? So this is going to be some sequence Sn, and then we do the limit n goes to infinity of Sn, which could converge or diverge. If it converges, that means that our summation an converges, and if it diverges, that means the other one diverges. So that is what it means mathematically, if you're interested in mathematical proofs and so on, and definitions. But we are not going to use any of this that I wrote right now to calculate convergence of series. We are going to learn 10 tests in 4 sections, and then it will be like figuring out what is the appropriate integration technique. You will figure out what is the appropriate test to use to test whether a certain part is a certain series is convergent to divergent. So let's take a look at first major test, which is known as geometric series test. Now, this is the stuff that you are memorizing. You are memorizing the form of the problem and the conclusion of the problem. So the form of the problem is, if it looks like this, it's geometric series. And then the conclusion is, you will look at R. If R is between -1 and 1, we have convergence. If R is outside of 1 and 1, we have divergence. This is how ridiculously easy this is. You look at the number and you just determine whether it's between two values or not. If you don't memorize this, you are doomed, because there is no other way to do any of this stuff. So I need this space to write something else here, but I want immediately to show just a quick example. So here I have 3 to the n from 0 to infinity. The way you solve this problem is you use your eyes and you look and you say r is equal to 3, which is bigger than 1, problem diverges, and you move on with your life. That's it, right? You will say diverges by geometric series. You don't have to write the word test. Diverges by geometric series.
We write down DFT.
What happened?
We write down by DFT.
You can if you want to. Fine. Another example, the same thing. You have, let's say, 4 to the negative n. 0 to infinity. You say, algebra. To have positive exponent, because I memorized there has to be a positive exponent there. Positive exponent, you have to peel off -1, which makes this into a quarter. And you say r is a quarter, which is less than 1, which is convergence by geometric series test, GST. There you go. That's it. When you recognize the form of the problem as geometric series, you memorized the geometric series form and you know the conclusions for it. There are no calculations here. There's nothing going on other than you memorizing this.
Professor, how did you turn that into 1 fourth? I understand that it's a negative.
Negative 1. 4 to the negative 1 is? Go on. Go on. All right. Now, for geometric series, if it converges, we can find the sum using the formula sum is equal a over 1 minus r, which is another thing you're memorizing here. Obviously, if it diverges, they add to infinity, so don't add them with the formula. So now you have your first test. 9 to go. So now I will ask you to tell me, since the bottom example is the one that converges, what does it converge to? What is the sum? What is the sum? 2/3? 4/3? So S is, A is 1 divided by 1 minus 1 quarter, which is 1 divided by 4 quarters minus 1 quarter is 3 quarters. 4/3. So it adds to 4/3.
Are you sure that, how can you know that A is going to be 1? It's going to be 1.
There is nothing here, right?
I thought it meant, oh yeah, I thought the number out front was the
1 quarter is R. A is 1, yep. So for me, this was fascinating. I didn't understand any of this stuff when I was doing this for the first time. But for me, it was fascinating to know that I can add infinitely many quarters and somehow get 4/3. That is, you know, if you add infinity, right, you should be getting infinity, but you're not. Not every time, at least. Which is great. So this is the time where we should take a look at some examples from the textbook. This is the first half of the There is one more part to 8.3. We're not done. So,
what happens if it goes 0, then it goes like 2, for instance? Then
what do you mean 0?
If it isn't over 0.
Oh, we'll deal with that. Yep. That's the scarier part. So, in a textbook, summation of 3/5 to the k goes from 0 to infinity. We don't have to write this k equals 0, we can just say 0, and it's understood that it's k that goes from 0 to infinity. So this is the textbook example, problem 20. Go on.
How many levels of algebra did you send in during class?
Probably 17.
Where are we at now? Is this still 3?
Oh, this is, you just look at it and you know what the answer is. We didn't have to do any magic yet.
No, I'm not saying this problem. I'm saying like what we're doing right now today. Tonight.
2, 2.5.
On a scale of 1 to 10, how hard do you think it is?
Well, this is the trickiest. This is a very good question. How hard do I think this is? When I was a student taking this chapter and the next chapter were the most difficult things I've ever seen in my life across anything, and I barely passed it. These 2 chapters, I barely squeezed out. I believe I had D on the exam when I took the exam 3. It was 3 weeks of regular stuff, and the reason was that I was trying to use common sense and I wasn't memorizing things. I was trying to reason with this stuff, which is the reason why I already told you 15 times. If you don't memorize this, you're doomed, because there is no reasoning with these things. You take a look at this, and there is 3/5. You know that that's the R position. A position is in front, and it's 1 in this case again. So now when you're looking at this thing, you say, okay, R is 3/5. I memorized that if it's between -1 and 1, right, it's convergent, and I am done, right, by geometric series test. And then I can also compute the sum, because it's convergent, which is A, which is 1 minus 3/5, which gives me 1 over 2/5, which is 5/2, and I can say convergent to 5/2. And that's the end of the story. And then algebra starts sneaking in with the problem that looks like, let's see, algebra sneaks in just a tiny bit. So here is the problem. This is a modified problem. It says 3 times 4 to the k over 7 to the k from 0 to infinity, right? So that's a modified problem. And you know, now we have to actually use a bit of algebra to solve this. So now, how hard is this for me? Right now, these two chapters are the easiest and most powerful stuff that I know and I deal with. But as a student, it was completely opposite. Because at one point, I just had a revelation, and it was like, oh my God, right? But up to that point, it was hell on earth for every single problem because I didn't understand any of it. It made no sense. Because I never memorized the tests, and I never utilized algebra to massage terms and examples into the form where you just sledgehammer done. That's how it goes.
How about your other students? How they do on this chapter and all?
Very well. Because vast majority of students actually listens when I say if you don't memorize this, you're doomed. And they memorize it and it goes well. And then we have those who will try to be smart in the other way, and then it's not going to work well. But for majority, it goes well because I emphasize it so much. And we'll see. So looking at this problem, I bring 3 over here, and I have 4 over 7 to the k. See, this is all manipulating algebra, knowing how the exponents work, and so on. If I have the same exponent over 2 different bases, then those bases are either multiplied or divided, depending on where you started from. And now, you have the form of summation A R K, right? So now we know A is 3, R is 4/7. R is 4/7. That's less than 1. Convergence. Done, right? So we know it converges. And then let's calculate the sum. A is 3. 1 minus 4 over 7. That's 3 over 3 over 7, which is what? Which is 7. So the whole thing adds to 7. Right? And now, let's take a look at this problem. It says summation of 2 times one half to the k from 1 to infinity. How much is A? This is such an evil question.
A equal to?
Nope. And it's nope because, see that? Anytime, so every aspect of this formula must be memorized, which includes that every series starts at 0. You have to memorize every single part. It goes to infinity, starts at 0, everything. Only then A is A. What I'm going to do now is mathematical procedure that has to be done every time to change that 1 into a 0, which would in fact change A at the outcome. R cannot change ever. R is 1/2. We see it's convergent. That can't change. But A changes every time if this is anything but 0. And here's how we do it. It's going to be substitution and algebra. We realize that this is k equals to 1. Remember this very well, especially those of you who are going to differential equations. K is equal to 1. I need that to be equal to 0. Common sense, subtract 1 on both sides. Right? So what we have is k minus 1 is 0. Call k minus 1 n. There's your substitution. And now, substitute on the other side. So now I have summation n 0 to infinity, 2 times 1/2, and k is n plus 1, right? Do we all see that algebra of substitution? You should be able to substitute by now because you're veterans in U sub, back sub, trig sub, right? So this kind of sum should not be a problem, right? No derivatives, at least. So one more time. Whatever non-zero number you end up over here is subtracted on both sides, and that is going to be 0, and you set this side to whatever variable you want, n, or t, or g, whatever. So now, your k minus 1 is n, so k minus 1 is n, which then is 0, so n is 0, but this k cannot stay there anymore because now our counter is n. Variable is becoming n. So you have to switch that k, so that you have to switch the u as well, dx, right? So what's k? Look at the formulas. K must be n plus 1. N plus 1. Plug that there. Now, we fixed the counter, but we messed up the exponent, right? Because, again, the only way the formulas in the universe works is if this is 0 and this is k. We got this to be 0, but we messed this up. So how do you fix that now? Well, luckily it was plus 1, right? So because it's plus 1, what do? We peel off 1/2. So this becomes 2 times 1/2 that we peel off, and 1/2 remains with n.
So how can we peel it off?
That's a plus 1.
If it's a plus 2, can you peel off a full?
Oh, yeah, because
Yeah, you peel off 2, so it will be 1/4. And that's next problem with a 3. So now, what is your a?
your A is 1.
1. Half and 2 cancel. And all you have is 1/2 to the n. So you see, convergence or divergence doesn't change with where you start your series, but the sum does. And you have to be very careful about that. So now we know it converges, right? And we know that the sum is going to be 1 over 1 minus 1/2, which is 2. A lot of face palms on this on exam. So be mindful, that little number there. Now, all of this that you just that you see now is called shifting the counter. And this is how it looks like in differential equations. Remember this stuff? So these are the power series. It's your chapter 9. Now this chapter is used, just need to find, there it is. So you start with a function like this. When you take derivative, it becomes 1, then you have to shift it back to 0. Look that the guts change, right? So the guts change because of that counter shift. Now what we are doing is equivalent to 13 plus 7 is 20, right? That's the next level on the next class. You will be able to do that by the time you get there, but you can't just say, this is going to be one problem that I can skip, and then because I really don't understand it. If you don't understand it, work double hard to understand it so that you can perform much tougher transformation later, which has yet another iteration of a tougher later, and so on. By popular demand, here is another problem. Feel special, right? Popular demand? Awesome. Summation of m goes from 2 to infinity. 5 over 2 to the m. Yeah.
So I have a plug-in against 5, 4 in or and like can't make substitute. You can plug in 2.
Good.
And I think converted by 4 for some.
Mm-hmm. Good. You got it. All right, let's do some algebra. So summation, we put 5 here, and then 1/2 raised to the m power. We still have m goes to 2, oops, and we know that we are supposed to subtract 2 on both sides. So -2 to make it 0. I'm going to have m minus 2 equal to 0, and I'm changing this variable m, let's say, into k. So the next step over here is summation 5 1/2. K goes from 0 to infinity, and since m is going to be k plus 2. So I need to peel off 1/2 squared, which is, as you said, 1/4, which gives us 5/4.
Hey, Professor.
Yeah.
Is that m's in the denominator, so how does...
Then 1 to the m will always be m, but 2 to the m, 2 to the m will be 2 to the m.
Yeah. So you have that, you have 1/2 to the m. You can put m over here out of nowhere, that's not a big deal, and then put the algebra together into this. So we have to peel off 2, which will be 5 times 1/2 squared, and then 1/2 to the m, which gives us summation of 5/4, 1/2 to the m. And as soon as I have that, I have everything. That's it.
Doesn't make sense how you got the k equals 0. And it was going through that.
Actually, what I wanted to write there is that m minus 2 is k. There we go. I'm defining substitution. That's definition.
These should be k's, right, in the algebra?
Yeah. These are k's. Like this. So we first subtract 2, then we see that m minus 2, we can call it k or t or n, whatever you want. And when you plug everything in, you get 5/2 at the end. So it's 5/4, let's say, divided by 1 minus 1/2. That's 5/4 divided by 1/2, which is 5/2. So we have infinitely many numbers that are adding to 2.5. Nice. And the last problem that you guys should work on is, drum roll, how much is 1/4 plus 1/12 plus 1/36 plus 1/108 plus ... forever? How much is this? So how would you go about figuring out the formula for this? Because we need to put it in a summation form, right?
We're trying to figure it out here, okay?
Is there anything that we can do? Any ideas?
The difference is the denominator times 2 added itself. I don't know how to point that to a AOR.
It's 1/3 being multiplied again. It's 1/3, but it's neither in power.
1/3. Well, 1/4 is not divisible by 3. What do you mean 1/3?
1/8.
Can we factor out anything out of all of these? 1/4. Okay, so start there. We factor out 1/4. We get 1 plus 1/3 plus 1/9 plus 1 over. Is that 27? So now you can call the first one 1/1, right? So what's the, for the bottom now, what is the pattern?
Denominator's being square half.
Do what?
This is less time by 3.
So,
So we count this way.
yeah, 1/3 to the end.
So that is your R.
1/3. Because look, if you have summation 0 to infinity, and you have over here 1/3 to the n, when you have the first term, when n is 0, 1/3 to the 0 is 1. That's the first term. 1/3 to the 1 is 1. 1/3 squared is 1/9. 1/3 cubed is 1/27. And there it is.
Converges.
Yep.
You forgot less than 1.
Yeah, I put 0. Oops. Cool, right? So you can convert these strings and so on. Next test. They don't make a big deal out of this in a book. They should. So test.
This is still 83.
Yep. Telescoping series. I just get to box that. It's a procedure. It's not a formula like geometric. It's a procedure that we use for the, oh, actually, I should, let me box the form. The form is summation of, let's say, bn plus 1 minus bn. Now, observe that I'm not putting any number down there. Can be anything. Can be 1, can be 0, can be whatever. It doesn't matter for this one. So if I don't put anything down there, anything goes. We don't have to do shifting the counter or anything like that. So for geometric, it must be 0. Otherwise, formulas don't work. For this one, it can be 5. It could be pi, whatever. Oh, can it be pi? No, because we count 1, 2, 3, 4, 5, right? We don't count 1, 2, 3, pi, 4, 6, 7. All right. Telescoping series. You will recognize telescoping series if you have subtraction like this. Let's do immediately example to learn the procedure. Summation from 1 to infinity of 1 over n minus 1 over n plus 1. So we see a subtraction of two series. And I would like to figure this out. Now, clearly, I can't plug all of the values and just add them and subtract them, right? What I can do is I can plug maybe first 4 or 5, and then after that plug more in general terms, in terms of n, and then send n to infinity. You remember how for improper integrals, when you had infinity, you replace that infinity by a finite number b, you solve the problem, you plug b, and then you shoot limit b to infinity, right? We're going to do the same thing here. We are going to add infinitely many numbers, so I'm going to plug in a bunch of these. And then for the tail end, where I'm plugging in n's, or k's, for n's, I'm going to replace the k as k goes to infinity in the limit to find the final answer. So here's what I'm going to do. I'm going to write few of these parentheses. So this is going to be n equals 1, which is clearly 1 over 1 minus 1 over 2. Then for n equals to 2, I have 1 over 2 minus 1 over 3. Plus, the next one is 1 over 3 minus 1 over 4. Plus, the next one is 1 over 4 minus 1 over 5. And then I get bored, right? I'm going to leave it there. Now, what I'm going to do for the tail end is I'm going to plug in values, finite values for n, but they're going to be k's. So I'm going to say the last term, let's do 3 terms over here. So the last term has to look the same as the first, as the problem, right? Because that's the last term. Except I'm using k's now. Because I am plugging in kth number down the line, right? You know how you count 1, 2, 3, 4, 5, 6, 7, and then you go 1,000,001, 1,000,002, 1,000,003, 1,000,004, right? So k represents any one of those far away crazy big numbers, right? That's what k represents. And then I'm going to take that k and shoot it to infinity in a limit. So I have this. Then the previous term will take away 1 from each k. So k minus 1, and then k plus 1 minus 1 is just k. That the term before that will take off 1 more k, right? Because it's a previous term. So you can actually put infinitely many of those if you want to, but there's no need. So let's see what I did. I did n equals to 1, n equals to 2, n equals to 3, n equals to 4, and then I say I got tired. Then I say for the tail end, right, the one at infinity, I'm going to plug in a finite value k, and the last term has the same form. And then term before that, each k minus 1, before that, each k minus 1, and so on. So maybe you need to put 5 or 10 of these. You can, right? Because you write the last one, and then one before, just subtract 1 from each k, one before, again subtract 1, and keep subtracting 1 if you want 10 terms. If you need 10 terms, actually, not want, need. We'll see why.
Does add 1 to each and every single term?
What do you mean adding 1?
Like k minus 2, then you plus by 1 with k minus 1.
I said we started here and we're subtracting. We're not adding.
Okay.
We start at the end and subtracting. Don't confuse things. Now look at this, guys. Negative half kills positive half. Negative 1/3 kills positive 1/3. Negative 1/4 kills positive 1/4. That means that this one will cancel here. Look at the tail end. Negative k plus k, right? You see they all die? What's left? What's left is 1 plus the limit of negative 1 over k plus 1, where k shoots to infinity. What's this limit? Boom. Converges to 1. So we calculated the whole procedure, right? Everything went fine, and we were able to do this. Now let's see some of the examples from the
How can it be
book.
1? Isn't it 0?
There's 1 over here. Plus limit is 0. 1 plus 0 is 1.
No, I thought you said that the then when it goes to the plus by 1, it's going to be 0 plus by 1 divided by negative 1.
What negative 1? There's no divide by negative 1.
Negative 1 divided by 0 plus by 1.
K is infinity.
Yes.
Infinity plus 1 is infinity. 1 divided by infinity is 0.
Okay.
In the limit. Let's try more interesting problem. Let's say we have, oh, it's too early for that one. I'll make up one more before we drop the, how about summation 2 to infinity of three over n minus 1 minus 3 over n plus 2. First off, these 3's have to be the same for the whole thing to work. And also, if 3 is featured in every term, you can kick it out in front of the sum if you want to, because that's called factoring in algebra, except now you're factoring infinitely many terms, but it's the same concept. Whether you're factoring 2, 3 terms or infinitely many, it's the same thing. So you could start off this problem by kicking out 3 and then working the rest. There is no need to shift the counter. Our first value that we will plug is 2. So let's go. We have 3 times, and now a whole bunch of parentheses. The first term is n equals to 2. So when you plug in n equals to 2, you get 1 minus 1/4. Next term is n is 3. You have 1/2 minus 1/5. You see that nothing cancels, right? That's okay. Be brave. Keep pushing. 1 over 3 minus 1 over 6 plus still nothing. Still nothing cancels, guys. You see that, right? The next one is 5. It gives me 1/4 minus 1 over 7. You have 1/4. It starts canceling, right? We have 4 parentheses. We just got the first term to cancel. Now next one is 1/5 minus 1/8. We got a winner, right? And then plus 1 over 6 minus 1 over 9. Plus 1 over 7 minus 1 over 10. You know when you stop? You stop when you hit the first parenthesis that will cancel both terms. You see how 1/4 cancels a quarter, and then a 1/5 cancels here. and then a 6 cancels there, and then this 7 is the first time when you cancel in the same parenthesis. That means when you hit that point that all of the other ones will immediately cancel in your dot 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 part. That's where all they cancel. Now you have 1, 2, 3, 4, 5, 6, 7 parentheses. That means 7 parentheses backwards to see the same cancellation in a K domain. Right?
How do you cancel out the 1, negative, 1, 10?
That will be in here. Because it's guaranteed, because once you hit the first parenthesis that cancels in your pattern, every next parenthesis will cancel in the pattern.
Okay.
So look what survives, guys. Number 1 half, and number 1/3. And then we have to do 7 parentheses backwards to see what survives, because we have to take that limit of K going to 0, well, to infinity. So now we set up, we know from the first part that we need 7 parentheses. So I'm going to set up 7 of those. And I'm going to write them by using the 1 over K minus 1 minus 1 over K plus 2, I said. Yep. And now go backwards and fill all of the parentheses by subtracting 1 from K. So 1 minus K minus 2 minus 1 K plus 1. 1 minus K minus 3 minus 1 over K. Next one. 1 over K minus 4 minus 1 over K minus 1. 1 over K minus 5 minus 1 over K minus 2. 1 over K minus 6 minus 1 over K minus 3. 1 over K minus 7 minus 1 over K minus 4. So minus 1 on every K going backwards, and now go cancel. K plus 2 doesn't cancel anywhere. 1 over K minus 1, there they are. They cancel. K plus 1 has nothing, but K minus 2 does. 1 over K has nothing. It's like playing bingo, right? I call a value and you go, oh, it cancels. K minus 4, yep, there it is, K minus 4. We hit the first parenthesis that cancels both. As soon as you hit the parenthesis that cancels both, every next one will cancel here in this mesh.
Where do you get the K minus 1 and K minus 4?
What?
Forgot the minus.
Oh no, that's the computer. Look, it erases things. This is the problem. When I have it synced, it, for whatever reason, it erases stuff that I write. So what is this equal to? Yeah. What is this equal to? It's equal to 1. Everything that survived, plus a half, plus 1/3, plus the limit K goes to infinity of the terms that survive here.
What about that 3?
I don't know.
Oh yeah, there's a 3.
So you got those first terms from the parentheses above, the stuff that survived in the beginning.
Mm-hmm. So the stuff that survives in the beginning is there, and then stuff that survives at the end
Elemental.
in the limit.
is 300 by 3 since like you also need the limit to the limit.
Well, it doesn't matter because all of the limit terms are going to go to 0 in this case. Not every problem, but in this particular problem, they all go. So what you see here, each one of these, because the limit is in denominator, infinity, they all go to 0, so we don't have to worry about them. We just need to add the front. That's 3 plus 3 halves plus 1, which is 4, 5.5. Telescoping series. It's awesome.
Like how do they all go to 0? You probably are wrong. And then
1 divided by infinity is
0, 0. Okay.
Apparently you like this one, right? Let's wipe that smile off your face.
It's either a smile of joy or pain, but it's a smile either way.
Problem 57. 1 over k plus 6 times k plus 7 from 1 to infinity. Is this in a form of telescoping series?
No.
Good.
Not geometric series.
It's not geometric either. So what now?
You will want to do the partial fraction decomposition.
Yeah, partial fraction decomposition. Nice. Nice. Let's go. Let's get busy. Partial fraction decomposition to change this into the telescoping and then do telescoping. Now, before you go too crazy, I just need to show something which I realized on my own way after the class was over, actually a year later. These telescoping series, they show up all over the place. But look at this, guys. You see how over here, in the first parenthesis, you have n, and then n plus 1. How far apart they are?
Plus by 1.
1, right? Look, you have 1 surviving, and the next parenthesis killed everything. Look at the next example. How far apart are they? 3. How many parentheses survived? 3. And then start dying. So you will immediately know how many parentheses survive on front and the back just by how far apart n's are. But then you run into the next problem which says 3n plus 1 and 3n plus 2. Oh, are they 1 apart or they're 3 apart? So these are the kind of things that you do with the homework, right? You know, it's Sunday, nothing else to do. You sip on the coffee and keep cranking these things.
Like a cardboard puzzle.
Yeah. How's the partial fraction decomposition going? Good. Make sure you don't forget, because differential equations, inverse Laplace transforms, partial fraction decomposition again. And inverse transition.
So as long as there are difference.
Yes, it's correct form to the partial fraction, right? Yes.
Okay, no one's going to pick the one they can't go to the curve with. So you said if they cancel the curves, then they cancel all out. Then
Yeah.
like and
Just beginning, we're learning. You need to see that. I said that because I discovered that pattern. No one told me that. I saved you some pain, but if you write 3 or 4 terms, you will see that actually that's what's happening. Rather than just take my word for it. I can't wait for somebody who doesn't know this at all to be like, everything cancels, that's easy. And I see all the slack. So as soon as you...
Are you reading one of the universities where they say what should be your
but
So as soon as you
Keep the first one.
as soon as you have one set, if you start to think, see, how do you, so you should just be,
Got it?
like noise cancels on the outside. They cancel.
so I think I went too far there.
But then
Like, I need to want to stop.
there's only like this one. It's like 1 divided by 15 comes by
So
six.
this form should look weird. Whatever. And you just so I just gotta throw the puppy in the matches. Okay, so I'm here.
Okay, then should I do like 1 divided by n plus by 5? 1 divided by n.
I'm gonna write it off. Yes.
All right, guys. So this is how I'm solving this problem. Equals to insert partial fraction decomposition here, and that equals to the summation of 1 over k plus 6 minus 1 over k plus 7, right? Is that how we have it? We are starting this journey at 1. So the first parenthesis is 1 over 7 minus 1 over 8. The next one is 1 over 8 minus 1 over 9. The next one is 1 over 9 minus 1 over 10. But then we can stop because we immediately see they all, right? They all cancel. You look at the tail end. I'll set up 3. The last one is, you can't use k now. You can use whatever other value you want. So I'll use t plus 6, t plus 7, t plus 5, 1t plus 6, t plus 4, minus 1 over t plus 5. And if you look at these, cancel, cancel, and this one will have to cancel over there. So the whole problem is equal to 1 over 7 minus the limit of 1 over t plus 7 as t goes to infinity. And you got your 1 over 7 that you all have. Through partial fraction? Nice. What?
People wondering how come it takes like a short time, and then like the ones that Alki identified that was going to be the limit that you have to use.
What do you mean limit that I have to use?
1/7 that it wasn't going to go cancel. You're going to use it.
But do you see any 1 over 7 to cancel it? It's not what I'm picking, it's what's left after cancellation. What's left and the problem. We are not picking anything. We are just working with what's left after cancellation. So 1 over 7 stayed, everything else canceled, and then the last term stayed. We take the limit as t goes to infinity, works out to be 0 in this case, and we get 1 over 7.
Okay.
One more telescoping and then break. Tricks up? There's no tricks up. Ooh!
Like that. You know you're gonna wait till the complete term.
Enjoy while it lasts. Oh! Whoops. Sorry. Is it telescoping?
No.
Yes, it is.
Well, it is, but you can't do anything with it yet.
It's not in that form yet. So what do we use here? The boss, right there. She'd go on the top of the stairs. Yeah. Do we remember the ln formulas from pre-calculus 1, where the quotient in the argument goes into subtraction of two logs?
Yeah, L and k plus 0.1 minus L and k.
Yep. And then start cranking numbers. I know, but just remembering this problem after knowing all 10 tests, and you see this at the end and you go, the hell, what is this?
So you don't have to have difference in the
Exactly. Because remember, all the difference and addition, right?
yeah.
The difference allows you to subtract. So if you're getting, you need to get the plus there, right? You use plus, right? If you cancel telescope, is not there. I have a conceptual question, since you are cranking this. It's just mechanics. Imagine the previous problem and you work out partial fraction decomposition and you get a plus in between. And presumably partial fraction decomposition is right. Are we telescoping then? No, not minus, nothing cancels. That will most likely diverge. Might be another test you can do instead, but there are comparison tests and other things you're going to see, but that minus sign is crucial. It's the only thing that allows you cancellations here, which makes method possible. So yeah, partial fraction can get you a plus there, in which case this method is not good for that problem.
Okay, that's the same one we're working towards in the distance. You just need this without inside. We know anyway, the distance that it's in the one.
So once you get one parentheses worth of cancel, everything
After that,
the first one,
okay.
everything after that is gone, the second example, everything before that is gone. Okay.
Immediately is done. How much is ln1? Good. It's looking good, right? So we have 0 on the first.
Still smile.
Still smiling? Awesome. Bye, stream.